Hey guys, this is Jay. The concepts we'll be talking about today are proton NMR and carbon-13 NMR. Let's review over the number of signals that a molecule will produce from proton NMR. The number of signals equates to the number of chemically unique hydrogen atoms. So for example, this molecule would have 2 signals because it has 2 chemically unique hydrogens. As mentioned in our previous video, coupling or peak splitting can happen in proton NMR. And there are 2 general rules. The n+1 rule, which says the number of peaks equates to the number of neighboring chemically equivalent hydrogens plus 1. And the 3-bond rule. Hydrogens only couple when they're within a distance of 3 bonds. There are exceptions, but they're not common in this class. Here's an example. The hydrogens in the red box have 2 neighboring chemically equivalent hydrogens. By n+1 rule, they will produce a triplet. The hydrogens in the blue box are too far away from the hydrogens in the red box, as they're more than 3 bonds away. The hydrogens in the purple box have 3 neighboring chemically equivalent hydrogens. By n+1 rule, they will produce a quartet. The hydrogens in the blue box have 0 neighboring chemically equivalent hydrogen. By n+1 rule, they will produce a singlet. We ended the previous video with this question. What kind of signal will we expect from the red hydrogen? This is an interesting one because the 2 neighboring hydrogens are not chemically equivalent. One to the left and one to the right here. So we can't just use the n+1 rule and call it a triplet. Note that the n+1 rule still applies to neighboring chemically equivalent hydrogens. So we would use this rule for each set of chemically equivalent hydrogens at a time. For instance, the red hydrogen would get a doublet from coupling with the blue hydrogen, and it would get another doublet from coupling with the green hydrogen. Thus, the red hydrogen would have a doublet of a doublet. When chemically equivalent hydrogens couple with a hydrogen, they would have the same J value. We can think of chemically equivalent hydrogens as they're splitting the same way, as we can see here on the left. From top to bottom, one hydrogen splits here into 2, the second hydrogen splits here, the third hydrogen splits here, and so on. Because they split the same way, some possibilities in the middle converge, giving us the n+1 rule. When chemically inequivalent hydrogens couple with a hydrogen, they would have different J values. They split differently, and they would not converge, giving us complex splitting. Here's another question. Would the red hydrogen coupling with the blue hydrogen give us a greater J value? Or would the red hydrogen coupling with the green hydrogen produce a greater J value? The red hydrogen coupling with the green hydrogen would produce a greater J value because they share a trans relationship. And the red hydrogen coupling with the blue hydrogen will produce a smaller J value because they share a cis relationship. So in essence, hydrogens sharing trans have greater J value versus hydrogens sharing cis have smaller J value. Okay, so NMR is not only used in protons. It can be used for other atoms as well. And one of them is carbon-13. It has some similar characteristics similar to proton NMR. The number of signals equates to the number of chemically unique carbons. And the chemical shift trend is the same. Deshielded or more downfield carbons have higher chemical shift, and shielded or more upfield carbons have lower chemical shift. And there's some different characteristics from proton NMR. The magnetic strength of carbon-13 NMR is a quarter of proton NMR. And the typical chemical shift ranges from 0 to 220 ppm parts per million. Splitting is usually not seen, and there's no integration values. I also note that carbon-13 is significantly rarer than proton in nature, as there's only 1% of carbon that are carbon-13. So here's a picture where certain type of carbons will end up on the NMR spectra. We can see a general trend that more deshielded carbon have higher chemical shift, and shielded carbon have lower chemical shift. So similar to how electronegative group can pull electron density away, and leave hydrogen more d-shielded in proton NMR, an electronegative group can pull electron density away and leave carbon more d-shielded in carbon-13 NMR. Thank you guys for listening. See you next time.